Good day to everyone. So for today, I'll be discussing the preliminaries of linear programming. So in this lecture, I will be discussing a few concepts that we need to understand before we proceed with the graphical solution for linear programming problems. And to begin with, our title has the word linear. So it means we will be dealing with straight lines or lines. And in algebra, when we talk about straight lines, normally we are given the equation ax plus by is equal to c, where a, b, c are constants and x and y are our variables. So normally, uh, we have two variables involved. But of course, our equation can only have one variable. And in linear programming, we will limit ourselves with two variables only. But in algebra, it was learned before that as long as the highest degree or the highest exponent in your equation is equal to 1, then the equation is uh, repres the equation is representing a line. Then, in linear programming, we will try to consider also linear inequalities. So, meaning we can revise our equation ax plus by equals c, let's say as ax plus by is less than or equal to c, or we can also have, let's say, ax plus by is greater or equal to c. So again, we will be having first degree equations involved in linear programming. And also, in the applications later on, you will find that one limitation of linear programming problems is that we will have our equations or our uh, expressions involved will either be an equation or these types of inequalities, less than or equal, greater or equal. We will not encounter problems wherein we have strictly less than or strictly greater than. What else do we need to review in this section? We also need to review how to graph linear equations. So for example, we have the equation 2x plus, let's say, 3y is equal to 4. So if we have the equation 3x plus 2x plus 3y is equal to 4, to graph this on the Cartesian plane, so the Cartesian plane is composed of two axes. We have the vertical axis, the y-axis, and we have our horizontal axis, the x-axis, the point of intersection as the origin. So we can actually assign intervals here. So we can use, let's say, intervals of 1 unit, intervals of 2 units, 5 units. It depends. It depends on the problem that you are having. Now, the easiest way to graph a line is by considering what we call the intercepts. Intercepts are points of intersection of the line with an x-axis. So if the line crosses the x-axis, that's the x-intercept. If the line crosses the y-axis, that's called the y-intercept. So how do we do that? So going back to this equation, what we can actually consider is we can let in this case, we can let y be equal to 0. So if y is equal to 0, this will now be equal to 0. Solving for x, 2x is equal to 4. Divide both sides by 2, therefore x is equal to 2. Now, if we let x this time is equal to 0, so this will be equal to 0, y will now be equal to 4 over 3. So, if we will now plot those points on our Cartesian plane, so let's say I'll use this as 1 unit, that's 2 units, 3, and so on. So similarly here, 1, 2, 3, and then 4. So if you would like to label that 1, 2, 3, and 4, 1, 2, 3, and 4. Now, let's plot those points. So for this part, our ordered pair, x will always be first. We have 2, 0. And for this ordered pair, we have 0, 4 thirds. Plotting now those points on our Cartesian plane, x is 2, y is 0. It will be located here. The other one is 0, 4 thirds, or that's 0, 1 and 1 third. So that will now be the location of the point. And then, if we will now connect those 2 points together, the other point was here. If we will connect now those 2 points together, we create our graph. So that will now be the graph of the line 2x plus 3y is equal to 4. Next, the question is, if we will now try to modify, if we will now try to modify our, uh, if we will now try to modify our equation and convert it to an inequality. So let's say we now make this as 2x plus 3y is less than or equal to 4. So on our Cartesian plane, we have the graph of the line 2x plus 3y is equal to 4. This line is the graph of 2x plus 3y is equal to 4. So how do we now graph this? 2x plus 3y is less than or equal to 4. So this means now that if we take ordered pairs x and y and substitute it on the left side of the inequality, it must always be less than or equal to 4. So if you will look at the graph, actually, if it is less than or equal, we simply consider the portion of the graph below the line or towards the left of the line. So this entire region here, where the arrow goes, will now be the region wherein uh, points that you consider here must satisfy. Now, if you would like to check if your inequality is correct, you can get an arbitrary point here. So let's say I take the origin. Isn't it that the origin is 0, 0? X is 0, y is 0. Is 0 less than or equal to 4? The answer is yes, meaning our graph is correct. And when we are talking about 2x plus 3y is less than or equal to 4, where do we find the points? All the points on the line and all the points on this region will now satisfy this inequality. Okay? Just for your information, if this is strictly less than, you will find the graph that the line is a dotted line, meaning the points on the line are not considered in the inequality. But as I have mentioned earlier, for linear programming, our expressions would either be an equation or strictly less than or equal or greater or equal. Let's have another example. So this time, let's say we have the equation. Let's say we have the second example. Let's have the equation 5x plus 7y is equal to 8. Again, the easiest way is consider the intercepts. X is 0, solve for y. If x is 0, y will be, divide both sides by 7. This is 8 over 7. And then if y is 0, divide both sides by 5. X will now be 8 over 5. Okay, going now to our Cartesian plane. So let's say I use intervals of 1 unit. This is our x-axis. This is our y-axis. This is the intersection of the two axes. That's the origin. And let's also you have the scale for the y-axis. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So this will now have the coordinate 0, 8 over 7, and this will be 8 over 5, 0. So where do we find those? The first one, x is 0, y is 8 over 7. Where do we find that? 0 and a little greater than 1. So let's have that point there, somewhere there. The other one is 8 over 5, 0. 8 over 5 is again greater than 1. Okay, so somewhere here, there. And then joining now the 2 points together, we have this point here and the other point is there. Let me extend this and let's just change the color. We now have the graph of the line 5x plus 7y is equal to 8. Okay, next. What else can we uh, do here? Let's modify now our equation. So let's say, let's convert this to an inequality. Let's make this as 5x plus 7y is greater or equal to 8. So if we will now graph this, we want to find the region wherein if we take ordered pairs x and y, it will always be greater or equal to 8. Again, if we are considering greater or equal, so from the graph, what you do is you now get, since this is slanted to the left, you now get the section above. Or if you're facing the line, it's towards the right side of the line. So this entire region here, above this line, will now be the region satisfying 5x plus 7y is greater or equal to 8. Since this is greater or equal, the points on the line are included. So if you want to check, if that is true, let's get a point. Look at this. 2, isn't it that 2, 2 is above the line? Let's try to do it. If x is 2, this is 10. If y is 2, this is 14. 10 plus 14 is 24, greater or equal to 8. It's correct. So that will now be the reason. And then uh, it may also happen, we will also encounter in the problems later on what we call our negativity constraints. And for this one, let's say we would like to graph x is greater or equal to 0. Oops. X is greater or equal to 0. And the other one, is, let's say we have y is greater or equal to 0. So how do we do that? That's the y-axis. That's the x-axis. This is the origin. X equals 0. So x equals 0 is here. X equals 1, x equals 2, x equals 3, and so on. So greater or equal to 0. So we have our y-axis. So we have uh, the y-axis. So that's the line. That's the y-axis. Okay. And then we take the section towards the right. We take the section towards the right of the line. So that's the y-axis. We go to the right. So this entire section to the right of the y-axis will be representing x is greater or equal to 0. On the other hand, for y greater or equal to 0, y equals 0 actually will be represented by the x-axis, okay, and then greater or equal. So from the x-axis, we now consider the section above the x-axis. So that entire region will now be, so this entire region here will now represent y greater or equal to 0. Okay, so that's for graphing our inequalities. So another thing that we need to review before we proceed with our problems on linear programming is what we call locating our feasible region. And to consider our feasible region, for example, for this, okay, so let's say for this Cartesian plane, we have this as one condition given in the problem, okay? And then let's say for this condition in the problem, it's a less than or equal to inequality. So this will now be its reason, okay, for that inequality. So actually, that will be called as a constraint later on. And then let's say we have another one. Let me draw, let's say, this line here. And let me change the color. And again, let's say that will now be less than or equal. So it must now be towards this direction. That's the region for the second constraint. And then let's also have the non-negativity constraints. So this is now one of the non-negativity constraints. Okay. And since it will be greater or equal, so it must now be going to the right, going to the right, going to the right, going to the right. And then one last constraint, another non-negativity constraint. Let's now have y is greater or equal to 0. So that's y equal to 0. And then greater or equal, going up, greater or equal. There you have it. Those are the constraints. Next, how do we determine our, how do we now determine our feasible region? So to determine the feasible region, we look at the section where the planes or the segments or the sections do intersect. So this is one constraint going down. The red line here is another constraint is going down. Then we have the non-negativity constraint going to the right, non-negativity constraint going up. So if you will observe, the common region will be from this point, right? Okay. From this point until here. Okay. There. And then from this point going here. And then finally, the x-axis and then the y-axis. Thus, if we will now shade the entire section common, it will now be this part here. Okay, that's the common section of all the constraints. And this common section is what we now call the feasible region. And in this feasible region, we also have what we call our corner points. This is one corner point. This is another corner point. This is another corner point. The origin is also another corner point. Okay? So, after considering now those corner points, the question is how do we determine the corner points? Let me give an example. So, let's say we have these two equations. In algebra, it was learned also in algebra that you have several ways of solving the point of intersection of two given lines. So you have by elimination using addition subtraction, you have by elimination using substitution, or you have the Kramer's rule. I don't know if you are still familiar with those, but let's just introduce one solution. So maybe we can just apply solving the system using uh, elimination by addition subtraction. And in this system, we can now call this as equation 1. We can now call this as equation 2. And uh, elimination by addition subtraction, our target is to be able to eliminate one variable. And to be able to eliminate one variable, we must make the coefficients of the variable that we want to eliminate, so either variable x or variable y, to be equal. So in this case, we don't find a variable with equal coefficients. For x, in equation 1, 2. In equation 2, 4. Y in equation 1 is minus 3. In equation 2 is minus 2. So let's decide now to eliminate x. So if we would like to eliminate x, we would like to make the coefficients of x equal. So to do that, we are allowed to multiply a constant in a given equation. So let's say equation 1 will be multiplied by 2. That now gives us 4x minus 6y equals 6. And then we just copy equation 2. We have 4x minus 2y equals 10. So you will see here that we were able to make the coefficients of variable x equal. Now, since we would like to eliminate x, we can actually subtract one equation from the other kasi pareho sila ng signs. So to subtract one equation from the other, we now change the signs of one equation and then we proceed to addition. So 4x minus 4x will be 0, minus 2y plus, minus 6y plus 2y will be minus 4y, and then 6 minus 10 is minus 4. Divide both sides by minus 1. Y will be positive 1. And if x is positive 1, we can substitute the value of y in any of the equations. So let's say in equation 1, we get 2x minus 3 times 1 equals 3, giving us 2x minus 3 will be transposed, that will become positive 3. 3 plus 3 is 6. Divide both sides by 2. X will be equal to 3. Therefore, the ordered pair 3, 1 is the point of intersection of these two lines. And in algebra, we call this as the solution set. So going back to the previous slide, if we now consider this as one line, the red one, and if we consider the blue one as a second line, this corner point here is a point of intersection of the two lines. And we can obtain the coordinates of this point by using what we have explained earlier, solving for the point of intersection. Okay, so please review these basic concepts because we will be using them as we will be solving an example later on of linear programming.